let's look at some additional practice problems as that relate to hemiacetals and acetals. So in our first one, we're just being asked to identify if they are hemiacetals or acetals. It'd be kind of nice to have a few practice that aren't either, so we could kind of work on that. So I would encourage you to make sure to look at a few where maybe it looks kind of like they are, but they're not. But so for these ones, we know they're going to be one or the other. So in looking at a structure like this, your acetals always contain oxygen, either a hemi or an acetal. And so locating your oxygens can be kind of a helpful place to start. So I see here, I have a line formula. So this is an implied carbon right there. And that carbon is attached right here to an OCH3 group. So that would be an alkoxy group or an OR group. So I have an OR group right here. And then directly bonded to the exact same carbon, and that is kind of a critical piece of the definition, it is also bonded to the same carbon, an oxygen, which is bonded to an R group, a carbon group. So because this is a carbon. So in the same way, this is an O, an oxygen bonded to a carbon. This is an oxygen bonded to a carbon. And so it is essentially bonded to an alkoxy group on that side as well. So if we have the carbon bonded directly to two alkoxy groups, that is an acetal. When we look at this one, and I locate my oxygens again, so here's my carbon, I see that it is bonded to a hydroxyl group, and that same carbon is bound to an alkoxy group over here. So we have a hydroxyl right there, and an alkoxy right here. So when you have one alkoxy instead of two and a hydroxyl, so really essentially instead of an acetal we have a hydroxyl, or instead of an alkoxy group we have a hydroxyl group, we're essentially halfway to being an acetal, and so we are a hemiacetal. Now here, looking at slightly different forms of compounds, so instead of looking more at line structures, we got kind of condensed. So here's my carbon, and it has an oxygen bound to a methyl group, so this is an alkoxy group, a methoxy if we wanted. And then here, directly bonded to the same carbon, we have another alkoxy group, an OR group. So if we have two OR groups, so OR if that helps, if we have two of them, two alkoxy groups, we have an acetal again. Now let's look at a structure that has both of those groups, but we would not classify as either an acetal or a hemiacetal. So this structure here. We have a hydroxyl group and we have an alkoxy group, but they are not attached to the same carbon. Carbon, this carbon has our alkoxy group, and this carbon here has our hydroxyl group. So these would be neither. It's not an acetal, nor is it a hemiacetal, because that's a really critical part of the functional group, that they're attached to the same carbon. So this is essentially, this is an ether right here, and it's an alcohol right here. So we have the cyclic structure that has a ether kind of substituent, and it has an alcohol substituent, but it is not a hemi nor an acetal. Number 2, what reactants could produce the following product? So the first thing I want to do is identify what kind of organic family am I looking at. Now, you probably know from the nature of this video that it's probably a hemi or an acetal, but if you didn't, you would have to do a little bit more thinking to go like, okay, what am I seeing, and relate that back. So we have a carbon group that is directly bonded to an OR, an alkoxy group, an oxygen single bonded to a carbon, and another essentially identical, so it has these two alkoxy groups. So this is an acetal. And the reason I think it's helpful to identify it as an acetal is because then we can kind of think then, how do we get to acetals from other organic families? So it's a two-step process, which we're going to look at down here, starting with aldehydes or ketones and then reacting them with an alcohol. So in terms of identifying what structure would this have originally been, this is kind of the base, right? Right here, these 3 carbons, like I'm not going to start with structures that have a lot more than that. This is going to be the part that was my aldehyde or ketone. Since neither of them are hydrogens, I actually know that it's going to be a ketone instead of an aldehyde. Some textbooks actually go ahead and distinguish hemiacetals and hemiketals, or acetals and ketals, and it essentially comes down to those originally derived from a ketone or aldehyde. I kind of like that our book doesn't, because it's just one unnecessary more vocabulary word, but you might run into that. So the ketone that could produce this would be our simplest ketone, whose common name is acetone. That could eventually generate this by reacting with some alcohols. And our alkoxy groups are what generate our alcohols. So the other reactant would be essentially our alkoxy group. We would need 2 of them, one for each, one for the addition reaction to make it a hemi and one for the substitution reaction to make it an acetal. But these are the 2 reactants that we could use to produce the following product. The first reaction to make it a hemiacetal would add a hydrogen here, and then the alkoxyl group there to this carbon, and then we'd lose that double bond, and then we could react it again. So these alkoxy, to get them back into the alcohol form, just think of the same structure and add an H to make it an alcohol. So these are our 2 reactants that could get us this acetal carbon, the product, sorry. Okay, write a 2-step equation for the addition of methanol to propanol to make a hemiacetal and then an acetal. Okay, so let's start with these reactants. So we have methanol. Oops, where'd my pen go? There we go. CH3OH, and I'm going to react it with propanol, which I'm going to draw this way. Propanol, so I know it's an aldehyde, and it is a 3-carbon aldehyde. 1, 2, 3, prop 3. Okay. So, and it tells me it's going to be 2 steps. So let's start with the first step, which is that addition reaction. So we have a reversible reaction that occurs under acidic conditions. Change colors, kind of map out a little bit what's going to happen. So in this addition reaction, we're going to lose the single bond between, the double bond between the carbon and the oxygen becomes a single bond. And then we get jazz hands instead. Open up the drawbridge, and now we have an opportunity for a single bond on both the oxygen and the carbon so that each end still has 8 valence electrons. The oxygen is going to grab the hydrogen, and the rest, which is this alkoxy portion, is going to get grabbed by the carbon. So let's redraw that. So I have my carbon. It's still bonded to that hydrogen, just like it was before, and it's still bonded to the CH2CH3 one. It's also still bonded to the oxygen, except it's a single bond instead of a double, and that oxygen also has a hydrogen, which I could do. I could just add the hydrogen, or I could draw it like that. And then you'll notice it's missing a bond. Carbon wants to have 4 bonds. That is our alkoxy portion, so the CH3 from right here, and the oxygen. So now I have, you'll see, it's the format of a hemiacetal, but it asks me to take it all the way, because this is actually a fairly unstable structure. But the next step, becoming a full acetal for a linear one, is more stable, so we get, whoops, I want to add another methanol. Since it didn't imply, I'm going to use a different alcohol the second time. So plus CH3, reversible reaction, acidic catalyst, switch to green. All right, so we are going to lose the hydroxyl group. that is going to leave. It is going to react with that hydrogen. So we're going to get water as a product, and it comes from that place. And then this, what's left here, which is my alkoxy group, because it's lost the hydrogen, but it has a spot there in the oxygen to bond to something, is going to replace this lost hydroxyl group. So it's going to come up here and bond to that carbon instead. And so our acetal product, or our final acetal that we're going to make here, is going to, let's see if I have room for it. We've got the alkoxy group we added in the first step. We have our original, what was a carbonyl carbon, and it still has a hydrogen on it. And that's how I can tell it started from an aldehyde, is this presence of a hydrogen still. And nothing happened to the other, the R portion of our aldehyde, CH2CH3. And the difference between the molecule we just had and the new one we're making is that we now have this alkoxy portion that bonded to it. So OCH3. And there I have, that's why it's an acetal, because it has two alkoxys bonded to the same carbon. So keep doing those kinds of practice problems. Practice moves are thinking to a more permanent type of memory storage. So you want to do as many practice problems as you can, and let me know what questions you have.